Hello, this is a tutorial video for LRES 510. The video will cover homework 2, and the first part calculates type 1 and type 2 detection errors using the data we generated during the plastic plant exercise in the field on Wednesday. You'll recall we searched for 3 species in a 40 by 50 meter grid with 5 by 5 meter grid cells each. And those 3 species were the creamy buttercup, the daisy, and the green dragon. The second part of the homework is calculating generalized linear models, fitting generalized linear models. We'll fit a Poisson regression model for count data, then we'll convert that data to presence-absence and fit logistic regression models. So on to the first 2 questions. So the first 2 questions in the homework deal with how well you sampled, how well you detected each of the single species, or all the species altogether, and each of the single species separately. So the first thing to do is open up R. I already have R open here on my computer. I'll move everything down. I have my working directory correctly set to homework number 2. That has all the data and the homework script. If you need to download it, CD2L. So homework 2 is about species detection. And so you'll remember we searched and we compiled all the data into this text file, detection data 2017.txt. It's TXT is a tab delimited, is a text file, and this data file is tab delimited. So we'll read the table using the read.table command explained in the first homework and in some of the other tutorials. We named our data frame DD out of lack of a better term. And so first let's have a look at the names of the columns. And that is the year. We're keeping track of these year to year to year. We have, but this in this data set is only 2017 data. You had the site. Recall that we sampled at site 1 and site 2. We had the different columns. Those will be the columns that you search. So those can be 1 through 8. And the observers, the pairs of observers. In each of those, there are multiple pairs of teams of 2. Then we have this variable that we created called distance from road, and that's really just the distance of the 5 by 5 meter grid cell in order from 1 to 10. So 1 being the closest to where we started searching, and that was what we'll refer to as the roadside, and number 10 being furthest away. You'll recall at site 2, this was very straightforward. The road was just below us. At site 1, we talk a little bit about, we sort of say that there was a road that used to exist at the beginning. Finally, we have the 3 species and then the density of those 3 species. So how many individuals occurred in each 5 by 5 meter grid cell. So the first question in the homework is calculate your error. So you can find your observer in the DD $, your column in the DD $ observers. And I today will play the joker. And I will work through the first homework problem using the joker. The truth is the answer key. That's where we actually hid each one of the plants, so we actually know the truth in this context. So for question 1, I would like to know how well I located the different species and what my type 1 and type 2 detection error was. So here's how we're going to do that. And we're going to do it in quite a brute force way question, mostly so that we can work through the examples of understanding subsetting. And for the second part of question questions 1 and 2, question 2, I'll show you a slightly more complex way of subsetting the data. So if I'm the Mr. Joker, and I would like to know how well I detected the species. So the first thing, I'm at site 1 and then site 2. We'll let you do the data calculations for site 2 using this data that comes from this example. So the first thing I'm going to do is subset the data into just site 1. And you'll notice if we go look at it and we scroll through the data, we'll see that we have just the data from site 1. We can see that by doing this. So we know our DD subset 1 $site, and we can look at that variable. We can see there's only ones in there. Very good. So now we would like to know where the Joker did his data collection. And he only observed by just going and looking at, we can look at the 2 data frames. So DD1 $observers. We can find the Joker. There's some Joker at the bottom, and then there's the truth. So we know that Joker observed only column 1, or we could just subset here $observers equals column 1. Or sorry, got a step ahead of myself. We know that the Joker observed just column 1. And we found that out by looking at the 2 sites together. So cbind means column bind, so we're going to bind these 2 columns together, and this is just so that we can look at them together. So we'll say DD1 $observers and DD1 $column to find that out. And so now we can search through. Ooh, we have an interesting little unique thing that happened with within R here. So observers should be, we'd like to see it as dot character. We'd like to see the actual name, character, and we'll see it with the column number now. So now you can see we did it. This sometimes happens when you call up something in a matrix, especially a factor. It will convert it to a numeric category. So you can see Joker there, observed column 1. You can see what everyone else observed. And there'll be more repeats in there, and the truth has one total list. So we know that the Joker observed just column 1, because he was kind of lazy, the Joker. And now we're going to go and just subset. We're going to subset that to just column 1. So we'll get all the data from where it equaled just column 1. And now we'll go through and subset this data frame again that we called call.1, and we'll get call.1jk, where we get the Joker's observations. So we perform that subset. So what does this look like now? So we have just site 1, column 1, and we have just the data from the Joker. So here's what the data looks like, and you can scroll up through it and look at all the whole data set. So now we'd like to compare, so we have that data, so we want to compare it to the truth. So now we'll go calculate the truth, and we'll run that data set, and then we'll call up just that data set and look, and now we have just the truth for site 1 and column 1. So we're going to add the truth data to the Joker data frame that we have. And so we're taking this column 1, site 1, Joker subsetted data, and we're going to say $truth, which didn't exist as a column name before, but since we're telling it, it's going to be, we're going to tell it it's going to be called truth, and we're going to take this column 1, site 1, truth data, the density, so the number we observed, and add that to the Joker subset. So now we can run that and go look at the data frame. It's always good to have a visual look sometimes, so we can scroll up and look through. So now we have the Joker, the data, and we added this truth to the end. So that we took from the truth subset data and added it to the end. That will help in making the calculations a little bit easier. So now we'd like to obtain the difference between the actual number of plants in each cell and the number that the Joker observed. So we're just going to subtract the truth minus the density the Joker observed. So we can run that in this. There we get the number 0, 1, 2, 3, and we're going to save that as our error. So that difference will represent, whether we found negatives. So the negative difference between the truth and the actual, and then positives where we have found the truth and the actual, and then no difference between the three. So 0 would be no difference. A type 2 error would be when we found a species, but in truth it shouldn't actually be there. And type 1, we did not find the species, but it should actually be there. So we'll go through and run through these calculations quickly. So 0, too many plants. This would be a type 1 error. No errors. And then a type 2 error. We did not find the species when it was supposed to be there. So we're going to convert those really quickly. And we're going to convert those this way. We're going to take this data, our column 1 JK error that we added to the data set, and where we have zeros, 1, -1, 0, 2, and we're just going to take the sign of those. So the sign is going to give us -1 if it was a negative number, 0 if it was 0, and 1 if it was positive, so indicating the sign. So here we'll highlight that, and I'll just show you what it looks like. There's the two next to each other. So you see the +2, the +2 became a 1, the -1 stayed a -1, the -3 became a -1, and so on. So that will give us the, that will let us know where errors occurred. So now we can move on, and we can just, we can run the table, and we can now calculate a table of this. So there was a total of 7 -1, so 7 plots we were short, or 7 type 1 errors. We had 8 type 2 errors and 15 correctly observed. So now we can just run that and get the actual number of observations. And we know we had 30 total observations because we had 3 species, and there should have been 10 cells each. So that makes sense. So we had 30 data points. So the Joker had a type 1 error of 23%, a type 2 error of almost 27%, and 50% of the observations the Joker observed correctly. There was a plant where there should have been a plant. So now we'd like to have you guys do that for your observations. So really, you're going to have to duplicate the code above, starting up here. So you'll have to do this for site 1, and remember to change Joker to your observer. And then you're basically going to run through the same code, and then you're going to do the same thing, but change it to site 2. So in this first one here, calculate your error difference based on site 2, performing that different subset. So that's all pretty straightforward and gives you good ideas on manipulation. In the data set, it says who each one of the observers were. So note, repeat your second column at site 1 and at site 2. So do it for all the columns you observed. The Joker code gives you everything you need to know. You just really need to alter the subsets. So now let's move on to species observations, or species-specific observations, and what were the different rates of detection for the different species. So we're still going back to that original DD data set that we were working with. And I mentioned in the beginning that you can easily do this subset with less code. So now what we're doing, I'm going to play the Joker again, and we're going to do this for the different sites. So here's what we're doing. We're going to say, we're going to subset the whole DD data set, but this time we're going to subset it by more than one criteria. The first criteria is site 1. The second criteria is that the observer equals the Joker. And the third, because we know that it was just column 1, we get just column 1 data in here. That last column 1 subset is not necessary because we know the Joker, at least at site 1, only did one column. And that was the first column. So you guys can do that. You'll have to repeat it if you have multiple columns. So think that out a little bit. But now we're just gonna, so I did that for both the Joker and for the truth. And this time I'm going to do the same thing that we did above. We added this column truth, which is really just the density from the truth factor level. And now we can, let me run the code, and then we can look at our data frame. We can see, okay, now we have it by the 3 different species. And here's what we're going to do. Here's the easy way to calculate this with the least amount of code. So really what we want to do is calculate the Joker observed density, and we would like to know the subspecies, and we would like to calculate this for each of the species, and we want to calculate the sum because we know there should be 5 green dragons, 10 daisies, and 10 creamy buttercups. And we can verify that by just running this right here. Let's run this. This is just for the truth code, right? And if we take the sum, we know that it should always be 10 buttercups per column, 5 daisies, and green dragons. And we're just going to do that for the actual density observed by the Joker. Run that quickly. So it was 14, 5, and 3. So now if we just calculate that quickly, so the observed of the Joker divided by the truth multiplied by 1,000 or 100 to get the species, the percent of each species observed. And so we have way overestimate of creamy buttercup. We got the daisy just right, the Joker, but only observed 3 of 5 creamy dragons. So if that's a little bit confusing, we can go and you can do it the slightly written out broader way. Here's how we do that. So if we keep going with that, we can subset by each individual species. And so there'll be a creamy subset, a green dragon subset, and a daisy subset. And then we just do this sum again, except outside of t apply, and multiply by 100. So note the 2 different ways that I did it. This way here in line 140, and then this way in line 153 to 155. So hopefully that helps make sense. So all that's pretty straightforward. Remember, calculate for site 1, all the observed columns you did, all the observed columns you did for site 2, and then for each of the individual species. That accompanies homework 1. So now let's move on to questions 3 and 4, and those are going to be regression homeworks. So remember, regression is basically taking a whole bunch of data points and regressing it into one mathematical equation that captures the whole of the information. So basically we start with a line equation, y equals mx plus b, plus an error term. But this time, because we have data that comes in counts, we're going to have to use the Poisson distribution, which is just the natural log of y equals ax plus b plus the error term. So we're going to use the detection data, same detection data. I already had it read in, but you can always just do it again. It doesn't really matter. It'll just overwrite the last version. And now we're going to do a subset to get just the truth in this case. So we said subset observers equals true. And we'll run that, and notice I put a dot here at the end. And we'll get that dot, and then we'll just run this DD subset for site 1. So now I could have done it in a shorter way, but we'll look at it just in this way. So DD1 will be just the truth. We'll have this slide up. It's always hard to find the beginning here. Let's just do this. We'll do a cheater way. DD1, 5, 6. So hard brackets identify a specific point in the matrix. If I put nothing in for rows, it will show me all the rows. And now let's have columns 1 through 5. 1 through 5. And let's actually look at just rows. Let's look at rows 1 through 8. So there will come up. So you see we have our year, site, column, observers. And what's the total dimensions of the data set, DD1? That would be 7 column, 240 rows by 7 columns. So if we go back here, it looks like we have, I said 8, but we only had 7, or sorry, we had 240 rows. Here we have 7. So we'll add on the last 2. So now we have all 7 columns. And we have the density, the species, and the distance from road. So we're going to be fitting the density as a function of distance from road and then species. So here we go with our DD1 data set, a little bit of how to see the model, the species names. So we're going to do this for one species at a time right now. Again, we can fit a model that has species in it, so it wouldn't require us to do the subset. For this exercise, we're going to fit 3 separate models, one for each species. So first we'll subset the creamy buttercup, and that will be subset CBC, will be the name of the data frame. And now we're going to plot that CBC distance from road in response, or as a function of density. So we're going to have density. So it's an XY scatter plot where X is distance from road and density is on the Y-axis. So there's what the graphic looks like. We added our labels, note that sort of things. So now we'd like to fit a model to this to this data. And you'll recall in class we first started talking about generalized linear models. Today we're going to talk about generalized linear models. And they're specified with the function called GLM. And so our data, remember, is called CBC, and we would like to know we would like to fit a model where as density is a function of distance from road. And I mentioned before we're going to use the Poisson distribution, which is really just natural log of y, but it changes the way the equation looks and functions because you have to solve for y in these linear equations. So let's fit the data. So we fit model CBC1, and we can call up the summary of that model. And the summary will appear up here in your first one, and this just gives you a summary of the data. And so you can see we have an intercept term and a distance from road term. And the distance from road term is highly significant. And we won't worry about that probability of the z value so much up there. But because this is, well, I guess we will because it doesn't report the f value below. But basically it's a highly significant, basically 1 times, or 10 times 10 to the negative 8th. So a very small number. And we can look at the deviance in the model. So we know that the null deviance was 95 and their residual is 63 left. So we can roughly calculate that, 63 divided by 95. So we're explaining a fair amount of the variation in this case. There's, and we have 78 total degrees of freedom. So that's nice. We can see that the model is significant, but now we want to go and add the model to the line. So the first thing we're going to do is take that model and predict the response. And that will look like this. It will just come out as a line of vectors, but basically it's the predicted value of the line. So we're going to add that to our CBC data set. And we're going to call it pred for prediction. So let's run that. But the weird thing that happens is none of this is in order, and if we just added the line, it would not be in order of distance from road. So what we're going to do is order the CBC data set. So basically what we're saying here is take the CBC data set, and with CBC, order everything on distance to road, and we want to use all columns. The hard brackets indicate position in the matrix in this case. So we'll just run that. It worked just fine. There's some other ways of ordering it, but basically we just ordered the whole data set on distance from road, maintaining the values. So now we can go back and plot that again, and we'll add in our prediction line. We'll call up the window, and there you can see there's our predicted abundance in response to distance from road at site 1. So now you guys, here's the code for the daisy. It's just the same thing except a subset of the daisy, and we do the same thing and run the model again. And now we have the daisy, we have the prediction. We're going to take our prediction, and we're just going to plot our prediction based on those values. Call up the number, and you can see there's what the daisy density is. So actually a quite different pattern. So that's separating. We're not going to do it for the green dragons. The green dragons were too difficult to find. They had really low, correctly I found species, and we wouldn't trust it. But you guys need to do this for site number 2 now. Okay. So we're going to move on to the last question of the homework. But first we'll come to this. So you remember we just up there separated 3 separate models. Or we made 3 separate models, 1 for creamy buttercups, 1 for daisies, and 1 for green dragons. But it can also be fit in another way, and that's a 2-way ANOVA and with an interaction. So that's density in response to distance from road and species. And so we can call up those, we can fit that model. It's the same as we did before, except we didn't do the subset to get the individual species. Now we have all 3 species, and we can call up the subset. First, I'm going to type in ANOVA, and put in the all SP model, and hit enter. And you can see I get this sort of how much deviance is explained by each one. So the deviant distance from road explains 5% of the deviance. Species explains 18% or 18 points of the deviance, and the largest by far explanatory variable is the interaction of distance from road and species. So that means that if we have an interaction, we have this multiplicative effect where both the slope and the intercepts for the different species vary in response to distance from road. So now we can type in ANOVA again, and this time we would like to get a test statistic associated for each one of those. So our model is called all SP. We're going to say test equals chi. This is a Poisson distribution, and now we'll get 3 values. So distance from road is important, p-value. The other p-values are also very important. Note we got the same deviance number, and that accounts for how much deviance each one of those variables or interactions between 2 variables explain. So now we'd like to plot that, right? So this is essentially the same thing that we did above, except we made separate models, and now we have one model. So we're going to take the prediction from this all SP model and call it DD1 pred for the prediction again. And now we're going to order it just like we did before, based on species and by distance from road. It's not so necessary for ggplot, but we're going to do it anyway. Now we're going to load our friend ggplot again. Remember, if you should have installed it for the first homework, and you can just call library ggplot now. But if you didn't, you'll need to install the add-on package. So again, ggplot, the data is DD1. We have x equals the distance from road, y is color, y is density, and then the color we'll get by species, so each line, and we want to alter the point size, and I remember it's a little too big, so I'm going to change it down to 2. And then we're going to add the geom line that has the prediction for each species on it. So then we just run that code. call up the graphics window, and you can see here we got the calculated values for the different species. So this is Poisson regression, remember? It's a little bit, this gives you a good base for understanding how to take your fitted lines and put them onto the graphics, and also a little bit of the ANOVA evaluation. So now we're going to go a little bit further. And one of the most important types of regression that we use a lot is logistic regression. And that basically takes presence and absence data and we fit a regression model. But the logit function confines the response to between 0 and 1, allowing us to calculate a probability of occurrence or probability that a species would occur in a certain point. So it's really, let's use just one species data here. We'll go back to the CBC data that we fit. And we'll look at the CBC data. And this is just like what we did above. So there we have zeros, 1, 2s, and 3s, so integers. And we'd like to know when it's just presence, absence. So we're going to use this sign function again. It converts it to 0, 1, or -1. But because we have no negative ones, it'll just show up as 1 or 0. So now we have the binary presence, absence data. So we're not fitting anything that is focused on abundance anymore. So we're going to change this, add this to the CBC data, and that's going to be CBC $PA for presence absence, and we're just going to use that sign function. And then we're going to fit a generalized linear model. Again, in this case, we're going to have presence absence as a function of distance from road, but we're changing the family of the to a binomial error distribution family. So that's going to fit our logistic regression for us. Then we're going to, we can look at the summary, and the summary, oh, it's always hard. The summary gives us our slope and estimate values, and these are going to be in terms of the logit regression equation, which see the homework or see the lecture on YouTube about taking these values and putting them into the logit equation to calculate the probability of occurrence. But here we'll just show you how to graph it. And first we'll calculate the predicted values for the logistic regression, the same as before. And we're going to order them the same so that they plot nicely. And then we're going to add the predicted values, points and predicted values. So you can see there's the probability of occurrence of creamy buttercups as distance from road increases. So please repeat that for the daisy and maybe have used data from both sites. You can earn some extra credit points if you evaluate whether there were site differences. If you evaluate whether there are site differences, you will receive extra credit. Okay, that's it. This should allow you to do homework number 2. If you have questions, please post them into the discussion on D2L, and I look forward to seeing all of your homeworks and how you use this in your final projects.